So, what is an agent for us? First of all, an agent is an autonomous and intelligent entity. But for us, an agent is intelligence if it embeds a large language model and the agent uses this LLM to simulate a logical deductive reasoning. And exploiting this, the agent takes decision. This decision can be taken autonomously. And an agent, for example, can autonomously interact with a user. An agent can configure itself autonomously, simply dealing with the user in natural language.
Thank you for being here. I will run just a brief introduction of what we want to say and also who we are. Then I will lead the stage to Alessandro and Niccolò. So I'm Tommaso from Rome, as you may be hear from the sound, from the accent. Spindox is a company working in the ICT field. We are a group of more than 1,000 people in Italy. Of which 100 work in AI, as you can see from this introductory slide. I just want to introduce why we are here. So what we thought when we thought about the speech of today was, well, everybody will talk about LLMs. And that was the case. We didn't know for sure at the beginning, but we had kind of an idea of who would speak about what. Therefore, we thought, let's not talk about LLMs per se, but let's talk about how we use LLMs and agents to solve the good old-fashioned AI. This is a definition by Cambridge, GoFi. I don't know if you heard about it. And therefore, this is more or less the outline of today's speech. I will leave the floor to Alessandro and Niccolò, and I will talk about our framework for generative AI, how we use it to solve mathematical problems and to build simulation models, just to give a couple of examples. This is it.
So, let's start. First of all, you have to imagine a city where a group of funny but intelligent agents cooperate and they perform a set of tasks. For example, optimizing a process, forecasting important business variable, and so on. The purpose of this presentation is to tell you a story, the story of our journey in building a framework supporting this ecosystem of agents. So, our journey begins about 15 years ago when we started building AI-based solution for a decision support system. In this solution, we have always interpreted artificial intelligence through three fundamental elements: operation research, machine learning, in particular all the stuff related to natural language processing, and then finally simulation. The turning point of this journey has been the advent of ChatGPT 3.5, when in 2023, in February, OpenAI released this astonishing model, proposing to the world its capabilities. So we immediately understood that a paradigm shift was taking place. So we started in the creation of this framework, which helped us in delivering fast generative AI solution. At the beginning, the vision of the framework was a single agent vision, where an LLM coordinates all the activities. However, we quickly realized that this single agent vision could conveniently expanded in a multi-agent vision, where multiple agents collaborate with each other to accomplish a goal. So, in the early 2024, we started the creation of our framework based on an agent ecosystem. In the next slide, we will see the details of this framework and how we will use it in the old artificial intelligence stuff that Tommaso mentioned before. So, what is an agent for us? First of all, for us, an agent is an autonomous and intelligent entity. So now, without delving into the intricate aspect of defining what is intelligence, but for us, an agent is intelligence if it embeds a large language model and the agent uses this LLM to simulate a logical deductive reasoning. And exploiting this, the agent takes decision. This decision can be taken autonomously by the agents. And an agent, for example, can autonomously interact with a user. An agent can configure itself autonomously, maybe configuring its internal parameters and so on, simply dealing with the user in natural language. Then an agent interacts with the environment, exploiting AI tools. What are AI tools for us? For us, an AI tool is an instrument for a well-defined purpose that can be simple, for example, only for web navigation or web scraping, but for us they can also be complex analytical tool coming from the world of decision science, in particular optimizator or simulator. And what we do in particular is to build this tool in order to address the peculiarities of an optimizator and a simulator. Moreover, agents can get feedbacks from the interaction, can support decision, and can take action. So, for example, they can send an email, maybe shutting down a nuclear reactor. Just kidding, not a nuclear reactor. And for achieving a goal. So, this slide permits me to put emphasis to a particular topic that is important for us. So, the union of generative AI with the decision science world. We want to combine these two elements, where for us the decision science is operation research, simulation, and machine learning. We believe that generative AI can democratize the usage of these tools. We know how these tools are complex, are difficult to understand, but we think that exploiting these agents that can talk in natural language with a user, they can permit to understand analytical tool complex, and they can also permit to configure it in a more fluent and efficient way. So far, we have talked about individual agents, but what happens if we combine them? What is an intelligence ecosystem? According to us, it is a collection of autonomous agents working together and communicating and collaborating via a common interface. And much of the work inside the framework is developing this common interface. What there's behind the scene. There's a pub-sub communication pattern, there's a short-term memory, a long-term memory, all this stuff permitting the agent to share context. Then the last statement here, balance cooperation and competition to optimize outcome, it's another distinct element that I want to highlight. For us, there is not only collaboration in this ecosystem, but there's also competition. This permits us to exploit some interesting areas of operation research, like game theory. So we can put the agent in competition, not only in collaboration, into the agent ecosystem. Everything we've discussed so far has been condensed into a framework. And this diagram shows the main components of this framework. And in particular, during the next slide, we will focus on this central component called agentic pattern. Okay, no, you cannot see the... Okay, no, it's here. In that component, the ecosystem executes. Now, before delving into the details of the framework, I just want to give you an idea, an intuition about the three pillars on which the framework rests. First of all, fast delivery of generative AI solution with elementary building block. Then, a large usage of an interface segregation pattern in order to reduce the tech lock-in with the cloud provider. This is important stuff. So we are able to switch from a cloud provider to another without problem, and we can also create on-premise solution for this. And finally, cost-effective strategy exploiting math optimization. The second pillar is the usage and the union of a classic in 2 years ago, there's not a retrieval augmented system generation. So the union of a RAG system with a knowledge graph. This permits to add determinism to vector search. This permits us to be able to reply to qualitative and quantitative queries. And moreover, the knowledge graph permits also to add observability, also to match what we listened before about the explainability. Observability is a weapon that we can use to achieve XI. Last but not least, the agentic pattern. The agentic pattern is the third pillar, and we are going to delve into the details of this. So this slide shows the exploded view of the component that enables the execution of our agent ecosystem. First of all, we have the idea of a marketplace, which acts as a sort of primary interface of a user. The user access to the marketplace in natural language. They can chat with the marketplace. The marketplace itself is an agent, and the marketplace permits to discover, engage, track the performance of agents. Then we have two registries, one for agent, one for AI tools. They act as central repository storing essential metadata, for example, the purpose, the owner detail, the security roles, and so on. The core component is the agent ecosystem here in the middle of the slide, in which we have 4 meta type of agents. First, specialistic agents, designed for domain-specific tasks. Usually we use for this agent fine-tuned model and maybe smaller model. Then we have generalistic agents, which unlike specialistic agents, they are not domain-specific, but address substantially general purpose tasks. Here we use large models for these agents. Then we have operational agents focused on operational tasks related to monitoring, observability, data enhancement, management of the knowledge base, of the knowledge graph in particular. And finally, we have the orchestrator agents, which are responsible for coordinating and managing the interaction among agents. Below, you can see the AI tools, that tools coming from the decision science world, that are a sort of toolbox weapons for our agents. Okay, this diagram represents a user approaching the Spindox GenAI ecosystem with a simple request to perform demand forecasting for a food retail shop. to the aim to optimize both inventory and to reduce waste. The process begins with the user logging into the marketplace when he specifies his needs in natural language. All the interaction is a mixture of user interface and natural language. The marketplace identifies an orchestrator agent, in this case the forecast agent with a star above, capable of fulfilling the user requirements, exploiting the agent registry with a semantic search. When appropriate agent is chosen, an autonomous pipeline within the ecosystem is triggered. Then the forecast agent, in this case the orchestrator, takes charge, orchestrating the process and dealing in natural language with the user. So now is the forecast agent that starts interacting in natural language with the user. Maybe chatting with the user, increasing the context of the conversation, the forecast agent could identify the need for additional expertise, maybe in customer behaviors or market trends. At this point, the forecast agent starts to build automatically a tailored solution for the user. He understood the context, he understood the need for a specialist, he autonomously starts a semantic search on the registry. And in fact, it autonomously, for example, can identify the market trend agents, another specialistic agent, which provide insight for regional customer behavior and market dynamics. So, at the end, these two agents collaborate to reach the final goal of providing forecasting for the user. In essence, our framework automates a complex workflow by orchestrating a collaboration between agents. And this agent can be specialized or generalistic agent. And this permits to deliver substantially tailored solution to the user. Now I can leave the speech to Niccolò, that will introduce you how we use specialized agent in the world of both optimization and simulation.
Hello, everybody, and thanks, Alessandro. Okay, so Alessandro has outlined the framework of agents, and now we're going to see how we usually use it to attack optimization and simulation problems within our work and trying to automate as possible this process through the help of agents. So generally, when an expert starts an optimization problem, he has a problem specification, a context description, so he knows which answer we are looking for, and a description of the process we are dealing with. And often, if this process can be effectively represented through a set of mathematical equations, and we can easily identify variables that represent decisions that we need to make to guide our decision-making process, optimization can be a useful tool to give the answer that, for example, a client might be looking for. And this optimizer agent is able then to coordinate a set of specialist tasks that interact in a pipeline and somehow try to mimic all the logic process a human expert would make, starting from the problem description to reach the target solution. In particular, this framework, or at least a subset of this ecosystem with the agents highlighted in bold, were used in June 2024, and we participated at the Automated Math Reasoning Challenge at ICML, and we were awarded the first prize for track 3, and this was a good feedback that we were hedging in a good direction and motivated us even further in expanding and enriching our framework. So this is an example of the pipeline that was used during the competition. So we start from problem description, where there are data, there are some specific requirements that the client might have. And the first step that everyone does is start with formulating give a mathematical formulation of the problem, identifying which are the variables and the type of variables. Are they linear variables? Hopefully. Are they mixed integer variables? Identifying the list of constraints and the objective function that we might need to maximize or minimize. So we have a full representation mathematically of the problem. The second step, once we have a clear understanding of how we can represent the problem, is to extract all the data from the problem description, because from the mathematical representation, we are also aware of which one are the parameters we need to feed into the optimization model. And the data ingestor agent can help retrieving those information from the problem description. Once we have the theoretical formulation, all the data, we can start writing down the code in the preferred programming language. Can be in Python using Pulp or Pyomo, can be using the jump library in Julia. In this specific competition, they're required to use Pulp library in Python. So I'll write the code, and it follows the code execution agent that takes the code that is written in Python, try to execute it, usually catches a few errors. There's a feedback loop with the solver agent code. They can correct the code, and once we finally have a code that runs smoothly, the solution manager take care of collecting the solution and giving it to the user in the, let's say, in a structure that is compatible with the problem as it was posed by the user. And this is an example taken from the specific challenge. In this case, in this example, there is a wine company. They sell 2 products, and they want essentially to maximize their profit. It's a typical operation research problem. They have 2 products. We have a set of information. Each product yields a different profit, but we have some constraints either in demand or in supply. And so the first step, calling the math formulation agent, is to give a mathematical formulation. We can see that the agent is able to identify the 2 variables, identify the 2 set of constraints, and also to define the objective function that give us the total profit earned by the company given the value of the decision variables. Once we have a mathematical formulation, we can implement it, as I mentioned before, using Pulp library in Python. You can see it defines the problem, it creates the 2 variables, it sets the objective function, it sets the constraints, and then it solves the code. It required, in this case, a couple of loops of catching errors and correcting the code. And finally, it yields the final solution, which is the optimal share between the 2 products, and also providing some key insights showing that all the constraints that were specified by the user are actually satisfied in the given solution. So this was an example with simulation. In other contexts, the right approach to target or to give a specific answer to a question that the client might have might not be optimization. Sometimes we are dealing with very complex processes that can only be accurately represented through simulation. In this example, we are talking about discrete event simulation. And the client might want to know, usually, what-if analysis. I already have a model of my system as is, and I want to know what happens if a specific resource fails, what happens if a specific event fails, what happens if demand grows by 20, 30, 50%, so that I can anticipate decision and I can make informed decision for making my system probably more robust, for example. So in this case, the marketplace will direct us towards the simulation agent that, as before, coordinates a pipeline that includes several smaller level specialist agents that try to mimic, even in this case, the logic process that a human expert would take to try to find the optimal answer to the user request. So the first step is an intent parser agent, which takes the user request and try to convert it into a structured metadata, identify sort of mapping the request into some sort of simulation framework. and structuring it so that all the following steps are more robust because all the information is structured in a convenient way. Once all the information are clear, we start to plan all the operation. Usually in simulation, when we are modifying a model, there's a discrete list of sets that needs to implement it sequentially to reach the target goal, to reach the final modification of the model. Once all the list of modifications are clear, we can start actually editing the model one by one. And finally, yielding a validation to check if the initial plan was correct, if it was subdivided in a coherent number of steps, and if the results, and by result here we mean the modification of the model modified is coherent with the user request. If all is okay and validated, we can run the simulation, and an insight reporting agent can parse the solution. Usually simulations involves a lot of statistics, a lot of data that are not really easy to access by a non-expert. And in this case, we found out that LLMs are really proficient in extracting bits of information that help the user to actually extract the most from a complex solution. And this is an example. In this case, the user has a model and wants to know what happens to his system if there's a specific failure event at a given resource. In this case, it's the press station. And he wants to know halfway through the simulation. The planner identifies that it needs to happen halfway of the simulation. Here, the standard simulation time for the model was 16 hours, 960 minutes. And it correctly identifies that it needs to start this new event after 8 hours. Identifies also correctly that it needs to be a failure event and that it needs to last 2 hours, 120 minutes. Identifies correctly all the parameters he needs to extract from the information in order to set correctly this event in the model. And then he also recognized that he needs to associate this failure event with the specific resource. Once all of it is done, we can convert this logic description into specific changes that needs to be implemented in the model, in the specific library. Here is a library, it uses an extension of SymPy in Python. And finally, we can have a validation to see if all the modification and the final model modified is correct, and we can finally run a simulation and try to understand what happens to our system if this specific event occurs.
So now, let's go with a brief hands-on with the Atlante framework code. So we'll see a simplified version of the code. Otherwise, for the sake of readability, we should have a problem. So now I take again the before example. So we are going to reproduce the previous use case regarding a user asking for a forecasting solution. Above, you can see the user interacting with the marketplace, chatting with him in natural language. And behind the scene, the framework, first of all, instantiates a marketplace manager, which is an agent. And by default, this agent manager, who is able to dialogue with the user, and is capable also to understand the user intent. And as you can see, this assignment is done in a programmatic way. This is the programmer that assigned the agent to the manager. We will see in the next slide that this assignment can be also performed automatically via semantic search. So now the marketplace agent starts to identify an orchestrator agent using the method identify orchestrator agent here below in the execute method. In this method, the agent starts to analyze the user chat, so the context. To get the context here, Now it's a simplified version, but in the details, there's an analysis of what we said. We listen also with Piero in the first speech. So the short-term memory, the long-term memory has been analyzed, and also a sort of knowledge graph or conversation are analyzed in order to identify the intent of the user. At the end of the analysis, the agent has identified that the forecast agent as the most capable agent for fulfilling the user needs. Here we have the definition of the forecast agent. So the marketplace passes the ball to this orchestrator agent, who begins its execution by talking with the user for configuring itself. As you can see, proactively, the agent starts to ask questions with the user. What type of products do you want to forecast? Over what time horizon? And before passing to the next slide, note also the response of the user. I would also like to take into account customer behaviors in the area surrounding mine. It's from this sentence that the forecast will identify the user intention to analyze customer behaviors and in the areas surrounding him. So, in particular, it is through the get optional collaborators method that, exploiting a semantic search, the forecaster is able to search into the agent registry a specialist who can help him to satisfy the user needs. Also, you can see that the get default collaborators has been done in a programmatic way. Instead, the search for optional collaborators is performed via a semantic approach. So, the time is quite finished. So, I hope that I have given you the vision, the idea of how we want to combine generative AI to decision science, and more also an intuition about our framework is designed and it permits to execute agents ecosystem. So. Thank you all for the attention. We will be delighted to address any question do you have.